Swayam Prabha. Digital India. Educated India.
We have already discussed how to determine the signs of an op-amp in a circuit so that it's a negative feedback. Now, the circuits we considered had only one op-amp. Let's now see how to do it when we have multiple op-amps in a circuit and we don't know the signs of any of them. We have to determine the signs such that all of them are in negative feedback. And let me take some circuit. I won't worry about what the circuit is, and that you can determine for yourself from circuit analysis. But let me have a circuit of this type. Okay, maybe the circuit has an input voltage here and an output voltage there, but these are not relevant to determining the signs. We know that we will deactivate the inputs while determining the signs. Okay, and let me call this OPA 1 and OPA 2. Okay. Now, I will show the systematic procedure. After you have a little experience, you will be able to mostly simply by looking at the circuit, but initially you have to proceed systematically. Okay. Now, the procedure is still exactly the same as before. We remove an op-amp, we substitute the output of the op-amp with a test voltage and see what comes back to the input side of the op-amp. Okay. Now, you may run into a slight complication because of multiple op-amps and you don't know the signs of any of them. We will see how to resolve those issues. Okay. So, let me first determine the sign of OPA 1 and then OPA 2. Okay. The ordering has some influence, as we will see later. Okay. And Vi is set to 0, which means that this is connected to ground. We are determining the signs of OPA 1, that means that this is removed and I apply V test here. Let me call these A and B and I will determine VAB over there. Okay. Now, the rest of it is regular circuit analysis. The only thing is what to do about the other op-amp. Okay. So, we have this other op-amp also. So, how do we deal with that? The easiest thing is to assume that it's in negative feedback already. We don't know what the signs are, but it's operating as though it's in negative feedback. So, that means that its inputs are virtually shorted. So, in general, you assume that all other op-amps are in negative feedback, which means they have virtually shorted inputs. Okay. Now, this is the easiest thing. If you can do this, it turns out that you can't always make this assumption, but if you can make this assumption, it makes your life easy, because you don't have to worry about what signs the other op-amps had in the first place. Okay. Because whatever signs they had, the inputs are virtually shorted because it will be in negative feedback eventually. So, this is also at 0 volts. Okay. Now, I will later discuss what happens if you cannot make this assumption, but for now in this case it turns out that we can make this assumption. Now, in those cases where you cannot make this assumption, if you proceed with making this assumption, you will run into a contradiction. Okay. So, that is one way of kind of after the fact checking whether you can make this assumption or not. So, let us see what happens here if we do make the assumption. We have applied V test here this point is at 0. So, a current V test by R4 flows that way, and of course, nothing flows into the input of the op amp, and the same thing will flow into R3 as well. The voltage drop across R3 in this direction is this current times R3. So, the voltage at this point is minus V test R3 by R4. Okay. And now, between this point and VAB, we just have a voltage divider consisting of R2 and R1. So, the voltage here will be whatever the voltage is here, which is minus V test R3 by R4 times the divider ratio, which is R1 by R1 plus R2. Okay. Now, after you get some experience, you don't have to evaluate this explicitly, because you know that the sign is negative already. The ratio, value of the ratio doesn't quite matter in many circuits. But now we have determined that. So, this voltage is VAB, and according to the algorithm I described earlier, if VAB turns out to be a negative number times V test like this, then A is the positive terminal of the op amp and B is the negative terminal of the op amp. Okay. That will ensure that this op amp is in negative feedback. Okay. Now, once the signs for this op amp have been determined, we have to determine the signs for OPA 2. Okay. So, the signs for this op amp have been determined as plus and minus. Okay. And Vi is 0, which means this is grounded. Now, I will remove the second op amp and apply a test voltage like that. Okay. Right. Now, what to do with OPA 1? We can try the same assumption, that is that OPA 1 would be in negative feedback. So, its inputs are virtually shorted. But now, we will run into a contradiction, because let us assume that the inputs of OPA 1 are virtually shorted. So, that means the non-inverting input is at 0 volts. But if that is the case, the current here is 0 and the current over there, we have V test on this side, 0 volt on the other side, it is V test by R. Okay. And nothing flows into the op amp. So, you can see that Kirchhoff's current law is violated at this node. Okay. So, in this case, cannot assume that OPA 1 is in negative feedback and its inputs are virtually shorted. Okay. So, we have to try a different approach. Now, when the circuit is complete with this op amp, it will be in negative feedback and its inputs will be virtually shorted. But when OPA 2 has been removed and you replace that with V test, you cannot make this assumption anymore. So, in that case, you have to model OPA 1 as a voltage controlled voltage source, okay, with finite gain. Okay. So, let us do that instead. So, I said we cannot do this, right? We cannot assume that OPA 1's inputs are virtually shorted. So, instead what we have to do is we know that this is the positive and negative terminal of the op amp. Okay. So, this will be A naught times V d. right. Now, this is just the model for OPA1. OPA1 is in the circuit. OPA2 has been removed, and I will apply retest over there, and this time I won't make the assumption that the input terminals of OPA1 are virtually shorted. I just calculate whatever is there. By the way, Vi as usual is set to 0. So, now I apply Vtest here, and I have a voltage divider R2 and R1. So, the voltage at this point is Vtest times R1 by R1 plus R2. So, the voltage here is whatever this Vd is times A naught. So, it is A naught R1 by R1 plus R2 times Vtest. Now, at this point we have Vtest, at that point we have this voltage, and this can be calculated by as a linear combination of this voltage and that voltage. Okay. So, in general, if you have a circuit like this with two resistors and no current is flowing out of this, remember nothing is flowing out of this one, and if I have Va here, R3, R4 and Vb, you can prove this for yourselves. I will just write down the result. This voltage will be Va times R4 plus Vb times R3 divided by R4 plus R3. You have already found a result like this in some activity question or assignment question, and that is what we will use here. Okay. So, now what is the voltage here? In my case, Va is this Vtest, Vb is that whole thing. So, the voltage at this point, let me label these A and B. These are the inputs of the op amp OPA2. So, Vab would be Vtest times R4 by R3 plus R4 plus A naught Vtest R1 by R1 plus R2 times R3 by R3 plus R4. So, like I said, after getting some experience, you won't even have to write down this expression. The important thing is to see that the coefficient of Vtest here is positive. Okay. So, once you recognize that it is positive, you know that A has to be the inverting terminal and B is the non-inverting terminal. Okay. So, now OPA1 has signs like that, OPA2 has signs like that. Okay. So, a couple of points about this. You can find the signs of all op amps systematically by going through them one by one. Now, after a while, what happens is that if you design a negative feedback circuit with a number of op amps or any other stages, you will assign the signs so that negative feedback is valid once you learn this properly. Okay. But the most important thing here is to remember that all the nice properties of the op amp, such as virtually shorted inputs, are valid only if each of the op amps is in negative feedback, and you need to be able to make sure that this is indeed the case. The second thing is, sometimes it is said that, hey, the feedback comes to some terminal, that should be negative for it to be negative feedback, but clearly that is not the case. For OPA1, you can see that it is going through this stage and coming back to the positive terminal. Okay. And now, with the feedback coming back to positive terminal, OPA1 is in negative feedback, whereas OPA2 is the signal is going out and coming back to its negative terminal and it is in negative feedback. Okay. So, either way is possible. Finally, both of these op amps are in negative feedback. And just as an exercise, you can apply Vi here and then determine the value of V naught. Okay. Now, for ideal op amps, you can make the assumption that the inputs are virtually shorted, because we have already determined that the op amps are in negative feedback. So, the general algorithm is as follows. So, one by one you remove the op amp and you replace the op amp's output with a voltage source and see the polarity of the returned voltage to the inputs of that op amp. I mean, doing that calculation, you have to do something with the rest of the op amps in the circuit. The easiest would be to assume that all other op amps are in negative feedback, so their inputs are virtually shorted. Now, sometimes you cannot make that assumption because that will lead to a contradiction, that is, some Kirchhoff's law will be violated or some circuit law will be violated. In those cases, those op amps which are giving you trouble have to be modeled instead as a voltage controlled voltage source, which is the model for the op amp with a finite gain. Okay. And then you proceed with the analysis. And finally, sometimes you may have to resort to trial and error, because the op amp which you are replacing with the voltage controlled voltage source, you may not have determined its sign already. Okay. So, you have to consider both signs and then proceed. But eventually, there will be a unique solution. You cannot have different possibilities, right. For this circuit, for instance, this is the only possibility. So, if you reverse the signs of both op amps, you will find that one of the op amps will be in positive feedback. Okay. So, that is the algorithm in short, and you can use this for any circuit with multiple op amps. Okay.